All right, good morning. Good. I pulled out the calendar here just to show you that we have no class next Monday, and also you have no recitation next Tuesday. So as far as this class is concerned, you're done after today. You just got to talk your other instructors into canceling their classes. I already did that for you for this class. So no class next Monday and Tuesday. Now when we come back, we're going to be doing some truly exciting stuff. But you'll see it when you come back. Okay, today we're going to look at section 16.7. Surface integrals. So this is just like line integral, except we go one dimension higher. A line integral means you integrate something along the curve. Here we're going to integrate something along a surface, so just one dimension higher. Integrate something that could be the density, could be mass, could be whatever. And the formulas we'll be deriving will look very, very familiar to you if you remember line integrals. Okay, so let's take a step back to what we did yesterday. Suppose we have a parametrized surface. R of uv is x of uv, y of uv, and then z of uv. Last time we saw that the area, the surface area, area A of S, is a double integral over the domain of the parameters d of the magnitude of Ru cross Rv, du dv, or dv du. Okay? So you remember that quantity we integrate, Ru cross Rv, du dv, physically, this is the area of a small patch of the surface that we're looking at. So we're going to call this thing d capital S. So we'll define ds, d big S, as the magnitude of Ru cross Rv, du dv. And this will be the differential area, a tiny differential area element on the surface. Just like the d little s when we do the line integral, it's a tiny little segment of the curve. Here, d big S is a tiny little patch of that big surface. So that the area of that surface is simply the double integral over the domain of the parameters d big S, right? So that's our area. Okay, so with this definition here, now we can integrate something along the surface. So we integrate over the surface in a scalar field f of x, y, z. So we get a surface integral scalar field version is the double integral over the domain of the parameters f of x, y, z, d big S. So if you can calculate the surface area, you know how to use the parameterization, you know how to find RU and RV and cross them, then we're just taking one tiny step beyond that by integrating something other than a 1 along that surface. Nothing new. And of course, if f of x, y, z is 1, we get our surface area. Right? Of course, we get a surface area back if you integrate 1 along this surface. Just like if you integrate 1 along some curve, you get the arc length of that curve. Possible application. Suppose that this function we're integrating f of x, y, z is the areal density. Then if you integrate double integral over the areal density, you'll get a mass of the surface. Right? So for example, in most commercial airliners, the nose contains a weather radar and it has some kind of parabolic dome over that to protect that. And that dome is made out of aluminum with other stuff. How much does that dome weigh? If you could describe that shape of that dome by parameterizing that, you integrate the density of that material, then you find the mass of that dome. And of course, that has very, very important practical application. Okay, but as far as we're concerned here, all we're doing is just taking one tiny step beyond what you did last time by integrating something that's no longer 1 along some surface. The key is still in parameterizing stuff correctly. Okay, let's do examples. Let's calculate by the way, let me go back here. Normally, we don't write D here. We write the big S. So let me change that. So that's a double integral over the surface. In practice, we end up dealing with the domain of the parameters. That's D anyway, but normally we write it as big S. All right, back to here. Let's calculate the double integral over surface. And we want to integrate x, y, z d big S. And big S is the cone with the parametric equations x is equal to u cosine v, y is equal to u sine v, and z is equal to u. Now we're going to bound u between 0 and 1, and v between 0 and pi over 2. All right? All right, so this means the surface R of uv is u cosine v, u sine v, and then u, right? It looks like we're doing this in cylindrical coordinates. That's what it looks like. This looks like r, this looks like theta, right? Something like that. But the formula doesn't care what coordinates we are in. We're still doing the RU cross RV du dv. It doesn't care what coordinate system we are in. And the key piece here is just the same thing we saw last time. We got to find our two vectors, RU and RV. And we can do this very easily. And then RV minus u sine v, u cosine v, 0. RU cross RV. Let's see, what do we get? We get negative u cosine v, negative u sine v, and then u cosine v squared plus u sine v squared. Okay, so that's our RU and cross RV. Notice this thing can be simplified to just u. Because if you factor u out, then you get u times cosine squared plus sine squared. So that's really just u, right? So RU cross RV is minus u cosine v minus u sine v, u. And that's going to simplify the magnitude calculation. Square of this plus square of that plus square of that, all of that under a root. And then the first two things added together, just like this one right here, these things added together gives you u, 1u squared. So you have 2u squared, right? So 2u squared, which is the same as radical 2u. And of course, we only take the positive root because we're talking about the magnitude of something. So we keep the positive root only. Okay, so far nothing new. This is the same thing you would have done to find the surface area. Now we're going to deal with this xyz. And we handle this the same way you handle a similar line integral. All right, so now our domain, the two parameters, u goes from 0 to 1. V goes from 0 to pi over 2. And notice that because they're both bounded by constants, they can go in any order. That's why du dv or dv du are both okay. X, y, z. Now for x, y, and z, we're going to go back to our surface. On the surface, x is equal to u cosine v. On the surface, y is equal to u sine v. on the surface z is equal to u. So those three things will replace the x, y, z in here. Right? So that's my x, y, z. And then finally, d big S at the bottom of the last page. That's RU cross RV. So we're going to get radical 2 U. And I've decided to do V first. So I need to write dV du. So this guy right here, this is d big S. Questions? Right? Nothing too difficult here. All right, so let's integrate this stuff. Let's see, we have a radical 2 that we can get it out. 0, 1, 0, pi over 2. Inside here, I have 1, 2, 3 factors of u. U cubed. I'm sorry? 4? Okay, yeah, that's right. 1, 2, 4 of those. Sorry, 4. And then we have cosine, sine, and nothing. dV du. Okay? First round of integration is with respect to v. So that u to the fourth doesn't really do anything, stays put. How do you integrate sine v, cosine v? Substitution, right. And if you do that, you should end up getting 1/2 sine squared v and you can check, if you take the derivative of this, you get 2 times 1/2 sine v, chain rule, cosine v. All right, so that's what you get. All right, so the rest of this is really easy now. Sine at pi over 2 is 1, so that's really just a 1/2. So this becomes radical 2 over 2 times u to the 5th over 5, 0, 1. And of course, that's just 1 over 5, so you get radical 2 over 10. All right? And that's it. That's the surface integral over that cone, integrating x, y, z along that surface. Now, exactly what this means, well, one way to interpret that is that if x, y, z is the density of the material that makes up the cone, then this will give us the mass of that cone. Now, if this could be something else, but the best, I think that the simplest application to think of this is the density of the material that makes up the surface. Questions? Good? All right. Let's try this one. Integrate z over d big S, where S is the surface x is equal to y plus 2z squared between y is equal to 0 and y is equal to 1, and between z is equal to 0 and z is equal to 1. All right? So we're going to be integrating z of ds, where s is described by this thing right here, between 0 and 1 for y and 0 and 1 for z. What shape is this? I see we're still shaky with shapes. Now, the good thing about parameterizing the surface is that we don't really care, right? Because in the end, if you can parameterize this, we do our RU, RV, and integrate over that thing. We don't really even have to know exactly what shape we're dealing with. Because, look at it this way. Notice that y is bounded between 0 and 1. Z is between 0 and 1. So a natural choice for the two parameters are y and z, because they're bounded very, very simply. They're bounded by constants. So let's make them the parameters. You could make x one of the parameters, but then you're going to have to worry about, as y and z go between here and here, how is x bounded? You could do that, but it's going to be more complicated than using the more obvious choices of y and z here. So by the way, who can recognize the shape? Is it a paraboloid? Well, look at the x and z plane. We do get parabolas, right? But what about the x and y plane? We get a line of some sort. What is this thing? It's not one of the 6 that we looked at earlier in the semester. Again, doesn't matter, right? Even if you can't visualize this, can't really see what's going on, if you can parameterize this surface, we remove the geometric significance altogether and just do the integration. We turn that into a mindless integration problem. We remove the geometry. So let's do that. And arbitrarily, I'm going to let u be y, and I'll let v be z, just arbitrarily. And this surface right here, whatever the surface is, becomes, in the x component, is y plus 2z squared. Y is u, z is v, right? So the x component is u plus 2v squared. The y component is u. The z component is v. And u is between 0 and 1. And v is also between 0 and 1. Okay? So it still has a geometric significance, still some kind of shape bounded between 4 planes. But all of a sudden, we turn this into a problem that's purely calculus problem, purely algebra and calculus problem. Went from geometry to algebra. Because we know what to do next, we're going to take RU, 1, 1, 0, RV, 4V, 0, 1. Right? RU cross RV is 1, minus 1, minus 4V, and the magnitude of that, 1 squared plus 1 squared plus 4v whole thing squared. So that's going to be a 2 plus 16v squared. under a root. Okay? Okay, so now we do our surface integral. We're doing a double integral of z ds. We parameterize this. U and v both go 0 to 1. They can go in any order. 0, 1, 0, 1. They're the same. I'll decide what to do later. Z, look at the surface here. On the surface, z is equal to v, right? So we're integrating v. So that's my z. And then d big S. D big S is the magnitude of Ru cross Rv, which is 2 plus 16v squared under a root. And then let's just do let's do dv du. So that's a v, that's a u. That's d big S. I could have done du first, but I saw v is more complicated. I want to do it first. Do the easy stuff at the end. Right? How do we integrate this? Substitution. And you don't want to use u here. You're going to confuse yourself mightily with the other u, right? So let's use w. Well, let w be 2 plus 16v squared. So dw is 32v dv, 0, 1. And v is going to go to w now. So 0v means 2w for w. 1v means 18 for w. And this stuff is w to the 1/2. V dv is 1 over 32 dw du. Now look at this. The inner integral, no matter what this comes out to be, there's no chance it's going to contain a u. So it's going to be a constant du 0 to 1. So that outer integral du 0 to 1 really does nothing. Gains me a 1, right? This whole block is a constant with no u whatsoever. So really the outer integral with u is completely irrelevant because we're going to 1. If we're going to 2, then it becomes a 2. But here it goes to 1. Absolutely irrelevant. So we end up integrating, what is this thing? 1 over 48 to 18. So this is 1 over 48. 18 to the 3 over 2 minus 2 to the 3 over 2. Not a pretty number, but it's an answer. I think my blue marker is dead, so let's switch to green. Okay, so once again, if z is the density of that surface, then whatever this surface is, we never really identified it, but who cares? It's some kind of shape with this mass. Okay? All right, now let's do something a little bit more interesting. Let's integrate y squared d big S. And the surface we're talking about is part of x squared plus y squared plus z squared is equal to 4. That lies inside x squared plus y squared is equal to 1, and above the xy plane. Okay, now this is something we can visualize now. This is a sphere, radius 2, right? And this is a cylinder that goes up and down infinitely in the z direction with a radius of 1 in the cross-section xy plane. So we can actually get a very good picture in this particular case. So let's see. We're talking about, here's my cylinder, radius 1. And then I'm going to cap that with a sphere of radius 2. So there we go, right? It's a cylinder with a spherical cap at the very top. And that cylinder, not cylinder, the sphere, actually extends down, of course. And we only care about the part that's right above that cylinder, capping off the cylinder here. And below is bounded by the x and y plane. Okay? Now it's nice you can visualize that, but like we saw in the previous example, as long as we can find a good way to parameterize that cap here, then it really doesn't matter if we can see it or not. Because what we're going to be doing next is just RU cross RV, du, dv, and all that stuff. Okay? But because we can actually see what's going on here, it helps us in dealing with the situation and maybe decide on what coordinate system you want to go in. Okay, so first of all, let's check out the intersection here. We know this intersection is a circle of radius 1 because that's the cylinder that constrains the overall shape. What we don't know is at what height that intersection happens. We know the top of this is going to be 2 because that's the radius of the sphere, but we don't know at what height this happens. So let's figure that out. So right here, x squared plus y squared is equal to 1, and x squared plus y squared plus z squared is equal to 4, right? That means 1 plus z squared is equal to 4, so z must be radical 3. Okay? All right, so what do you think a good coordinate system would be? Looking at what is the surface that we really care about? It's a sphere. The cylinder is just bounding that surface. The one we really care about is the sphere. So what would be a good coordinate system to work in? Spherical, yeah. All right, so this is a sphere of radius 2. So rho is always equal to 2. What would the bounds for theta be? Theta is on the xy plane moving clockwise. 0 to 2 pi, right? What about phi? 0 to what? Pi over 2 puts me on the xy plane. I don't want to go that far. I only want that cap right above the cylinder. How do we figure that out? Yeah, exactly. Let's take a look at the projection of the YZ plane. Look at the projection onto the YZ plane. We see a spherical cap up here, and we see a cylinder bounding that. We only want this part right here. So that means phi can go from 0, which is straight up on the positive z-axis, all the way down to the intersection of the two shapes. Right? So now do you see why we can't go to pi over 2? Pi over 2 puts me down here, but I don't want that entire sphere. I only want up to this part right here. So we can figure out what phi can get to. So let's take this big triangle here. I want to figure out this angle. This is the maximum phi I'm allowed to have. How high is this vertical segment? √3, right. That's the intersection of the sphere and the cylinder. So that's √3. How about the horizontal one? 1. That's the radius of the cylinder, right? So that's 1. So now you can figure out phi. Taking an arctangent. Tangent of phi is opposite over adjacent. And this is clearly an angle that's less than 90 degrees. So an angle in the first quadrant with a tangent of 1 over radical 3 is not good. The angle is what? Pi over, you have 3 choices, pi over 6, pi over 3, pi over 4. Or 0 and pi, right? You can rule out 0 and pi over 2, okay? So we get down to 3. It's not pi over 4. That we know for sure. So we're down to pi over 3 and pi over 6. Which one is it? Sine is smaller than cosine, right? So which one would that be? Pi over 6. Very good. All right, if you had trouble figuring out that angle, that's not good. That's not good. Okay, you need to know that. Okay, so now we figure out our description of this spherical dome that's capping the cylinder. And here are the 3 numbers. All right, so let's describe our surface using the parameters u and v. And again, arbitrarily, let's let u be phi and v be theta. Completely arbitrary choice. So that means u is going to be between 0 and pi over 6. And v is going to be between 0 and 2 pi. That's a pi. So therefore, the parametric equation of that spherical cap to that cylinder, remember x component, x is equal to rho sine phi cosine theta, right? So x in our new names or variables, rho is always 2, we got that. X is 2 sine u cosine v. And y is equal to rho sine phi sine theta. So in our new variables, this would be 2 sine u cosine v. And z is rho cosine phi. So that's going to be 2 cosine u. All right, so once you get to here, because we parameterize this surface, yes? Sine, yeah, you're right. Oh, good. Because if I, thank you. Because next step would be all completely screwed up if we had gone with the cosine v. Good catch. Right? Okay, so now we parameterize this, we can actually completely ignore the geometric situation. Because once you parameterize that, everything that comes after that is exactly the same, regardless of the coordinate system, regardless of how you parameterize. RU cross RV, magnitude, DU, DV. Exactly the same. So from this point on, we're essentially on autopilot now, just taking the derivative and doing all the cross product. All right, so RU is 2 cosine U, cosine V, 2 cosine U, sine V, minus 2 sine U. RV is minus 2 sine U sine V, 2 sine U cosine V, and 0. Good. Good to see that 0. And now we're going to cross these things. It's not as bad as it initially seems. Because of that 0 here, it's going to make the x and y components all right, right? So in the x component, 0 minus that stuff. So 4 sine squared u cosine v. J component, 0 minus that stuff. But then we switch sign again. So 4 sine squared u sine v. The z component is a little bit annoying, but just have to work it out. There's no other way around it. We get 4 cosine u sine u cosine square v plus 4 sine u cosine u sine square v. And it's very nice to see the cosine square and sine square in the z components here, because those add up to 1. So this is the same thing up there, same thing up here, but these two added together simply turn into 4 cosine u sine u. All right? Okay, now we're going to take the magnitude of this thing. Again, it looks a lot worse than it really is because of the nice Pythagorean identity we can eventually use. It looks a lot worse than it really is, trust me. This thing squared, 16 sine 4th u cosine square v plus 16 sine 4th u sine square v. So these two added together reduce to 16 sine 4th, right? That's nice. And then this thing squared, 16 cosine square u sine square u, all of this under a root. Still looks bad, but it gets nice. 16 sine 4th u plus 16 cosine square u sine squared u What else can we do here? We're going to have to eventually integrate this thing. So let's find all the ways we can simplify this. We can take out the sine squared. How about 16 too? Yeah, let's take out 16 sine squared. So 16 comes out, becomes a 4. Sine squared comes out, becomes a sine, right? And then inside the root, this thing, we lost the 16, lost the sine squared, so sine squared remains. Second term here, lost the 16, lost the sine squared, cosine squared remains. And what's that stuff under the root? That's a 1, right? So I told you, this turns out to be something rather nice in the end. Okay? So that's the thing about trig stuff. Whenever you're doing this stuff with trig, oftentimes things will look horrible to start. But sometimes, not all the time, sometimes things end up being quite simple. Quite simple. Like in this case, this is really nice. Good stuff. Okay, now don't forget, we're still going to do the surface integral. All right, so what are we? We're supposed to do an integral over the surface y squared ds. And I've arbitrarily decided to do u last and do v first. Y on the surface is 2 sine u sine v. We want to square that. So that's a 4 sine squared u sine squared v, right? This is our y squared. And then ds is the magnitude, 4 sine u. And then d, what's this guy here? V, dv du. That's my d big S. Okay, and that looks like a horrible integration. It's, again, not so bad because 16 goes out, 0 pi over 6. First round of integration is with respect to v. So we have sine cubed of u, which I can move out. Sine square v dv. I'll put du here. Okay, because sine cube u du, all of that is constant as far as the first integration is concerned. So all of that goes out, and we're just integrating this. How do you integrate this? We've seen this quite a few times now. 1/2 minus, yep. Cosine of 2v, right? So that's this stuff right here. Okay, so that's doable. We don't have to worry too much about that. What about sine cubed of u du? How do you integrate this? Yep. We're going to factor out one of these guys out. And then we'll turn this into a cosine. And then we use a substitution. W is equal to cosine u. dw is minus sine u du, and so on. So that's how you handle that first integration here with respect to u. Second integration is this one. That's not difficult to do. Neither is that once you do the substitution. So after all of that, which we're going to skip, you get 32 over 3 minus 6 over radical 3. And it's a really stupid looking number, but it is what it is. Okay, notice, before you go, notice that even though we switch to the spherical system, We're still doing dv/du. I didn't do that rho squared sine phi thing. I didn't need to do that. After you parameterize, it doesn't care what coordinate system you're in anymore. It's always dv/du or du/dv. Don't supply extra stuff, even though it's in cylindrical or spherical. Just go with the basic form. All right, that's it. Have a good Thanksgiving break. I will see you not next Monday, but a week from next Monday.